By the end of this video, you're going to be solving these exponential equations like they're nothing, and in about 30 seconds, here's how this video is going to get you there. We're going to start by solving some exponential equations where you can find common bases. That'll be problems 1, and it'll be a little bit harder for problem 2, but then we're going to go over some problems where you can't find common bases, and we'll talk about how to solve those with logs, we'll deal with natural logs, and these problems will get harder and harder as we go. We'll eventually deal with some cases where we can't find common bases and both of the exponents have variables, and we'll do this one here that's going to involve natural logs and quadratics. So we're going to do all that, and then I'm going to give you a problem to try and answer in the comments. And by that point, it should honestly be breezy. And if you're looking for the notes for this video, and guys, I'm not just talking about any ordinary notes. These are printable notes, and I made them especially for you for this video. So if you're looking for those notes, I'm going to have them linked right in the description. Also in the description, I have an extra video linked where you and I will go through and solve 12 more exponential equations. So if you're looking to get more practice, especially if you have a quiz or a test coming up on this kind of stuff, I highly recommend you check out that extra video in the description. So starting with this first problem, how the heck are we going to solve for x? Well, it would be really nice if these two numbers were the same, because then we would know that the exponents are equal. And here's what I mean by that. If we had something like 3 to the x plus 1 equals, let's say, 3 to the 2x plus 5. Since these two numbers are the same, we would know that the exponents are equal. That has to happen in order for these two things to be equal. You can't have something like 3 squared equals 3 to the third power, where these two numbers are the same, but the exponents aren't equal, because this is 9 and this is 27. The only way for these two things to be equal, seeing as these numbers are equal, is for us to have the same power. So the only power that can go here is a 2. So you get a 9 on both sides. So that's what we're trying to get. We'd like to have the same number here and here. And well, okay, how can we do that? Well, what we can do is we can turn this 25 into 5 squared. And now we'll have a 5 on both sides. So we'll keep this 5 to the 3x plus 1. And then what I'm going to do is I'm going to take this 25 here, and I'm going to write it as 5 squared. And it's to the x plus 1 power, so I'm going to keep that. So we haven't changed anything here, right? I just replaced the 25 with the 5 squared. And now we have that 5, and you see that we have something to a power being taken to another power. And when we have that, we multiply the powers. So this is 5 to the 3x plus 1 equals 5 to the 2 times x is 2x, and 2 times 1 is 2. So we get 2x plus 2. And now that we have the same number in both spots, we have common bases is what we call it, we can set the exponents equal. And now that we have the exponents set equal, we can easily solve for x. So what I'm going to do is I'm going to subtract 2x on both sides to get all my x's to the left-hand side. And I'm going to want to get all my non-x pieces to the right-hand side, so I'm also going to subtract this 1 off. And so now I get 3x minus 2x, that's just x. And I have 2 minus 1 on the other side, and that's equal to 1. So for my first problem, I get that x is equal to 1. Moving on to problem 2, now how are we going to solve this? How are we going to get these two numbers to be the same? Well, our common base can't be like 8 here. We can't get an 8 with the 16 because it's not like we can replace the 16 with an 8 squared. 8 squared is 64, not 16. That's 8 times 2. And so you got to do a little bit of thinking, but what you might finally realize is that 8 is 2 to the third power, and 16 is 2 to the fourth power. And so we can actually make that common base be a 2. So I'm going to replace that 8 with a 2 to the third power, and it's to that 2x plus 12 exponent. And then remember 16, that's 2 to the fourth power. And I'm going to put that to the 3x minus 3 power. So now, again, I can multiply these exponents. So I have 3 times 2x, that is 6x. And I have 3 times 12, that's 36. And on the other side, I have 4 times 3x, that is 12x. And I have 4 times negative 3, that's negative 12. So now I can set these exponents equal because I have those common bases. So setting those exponents equal, I get 6x plus 36 is equal to 12x minus 12. now let's go through and solve for x. So what I'm going to do is I'm going to subtract 6x on both sides because I want to avoid negative numbers. So I'm going to move my x's to the right this time. And that means I need to move all my non-x pieces to the left. And so I'm going to add 12 on both sides. And 36 plus 12, that's 48. And so now all that's left to do is divide by 6 on both sides. And that will give me that x is equal to 48 divided by 6, which is 8. Great. Now there's one other thing I want to note here before we move on to the next problem, and that is that I'll copy this problem down here. Let's say that we didn't have this, but we had something very close. Let's say we had, instead of a 16, we had something like a 1 over 16. And we had a fraction here. How would we do a problem like this? Well, it would be pretty much the same exact thing. We turn that 8 to a 2 to the third power and get that common base of 2 with this one, but this isn't going to be 2 to the fourth power anymore. Now that 16 is in the denominator, we know 1 over 16 is a 1 over 2 to the fourth power, right? 16 is 2 to the fourth. And if we want to get this thing up to the numerator so we get that common base of 2, then what we need to do is make this thing a negative exponent. So we can replace 1 over 16 with a 2 to the negative 4. And that would be to the 3x minus 3 power. And then you would go through and do all the same stuff that we've just been doing. So that's how you deal with fractions in those common basis problems. I know that can get a little gross. And if you want to go through full examples of that with me, I go through more of those problems in the extra video, which I've linked in the description down below. So now let's move on to problem 3. Now problem 3 says that 4 to the x minus 3 is equal to 9. And okay, how could we get common bases here with a 4 and a 9? Well, we're not going to be able to do that here. And so, okay, if we can't get common bases, what do we do? Well, this is where logarithms start coming into play. What we're going to do if we can't find common bases, like in this example here, is we're going to take the log of both sides. And I'll show you why we're going to do that. But first, if we take the log of both sides, we're going to get the log of 4x minus 3 is equal to the log of 9. Now here's why we did that. Logs have a really nice property where if you have the thing that you're taking the log of, this is called the argument of the log, if that is taken to a power, what you can do is you can pull that power out front of the log and just have it multiply out front. And so we can rewrite this as x minus 3 times the log of 4. And that's equal to the log of 9. And by the way, if you're still a little confused on log properties, you're not sure how all that works, I have a whole YouTube video where I went through that. But yeah, getting back into this, how can we start solving for x? Well, what I see we can do immediately is just divide that log on both sides. You could think, okay, let's multiply it through, and that's fine, but it ends up creating more work for yourself. What we can do is we can divide by log 4 on both sides. And when we do that, this log 4 goes away, and we only have the x minus 3 left on the left-hand side. And on the other side, we have log of 9 divided by log of 4. From here, we can just add 3 on both sides. And that's going to give us our answer for x. X is going to equal log of 9 divided by log of 4 plus 3. And there we go. Now moving on to problem 4, we've got the same problem that we did in problem 3 where we're not going to be able to get common bases now. So what do? Well, when we can't do that with e, we do something pretty special. We're still going to use logs here. We're still going to take the log of both sides. But instead of just using a regular log now, we're going to use a natural log. And you'll see why that is in a second. Let's take the natural log of both sides. And that'll give us the natural log of e to the x is equal to the natural log of 5. And now let's use that same property of logs where the exponent can come out front. If we do that, we get x times the natural log of e is equal to the natural log of 5. Now here is why we use natural logs when we see an e. The natural log of e is just 1. And so we know that, x times 1, that's just x. X is equal to the natural log of 5 here. And if you want, you can throw that in your calculator and all that. And if you're not convinced that natural log of e is 1 just by me saying it, well, let's go through it. Natural log of e, whenever you see that ln, you can rewrite that as log base e. That's what a natural log actually is. And, well, that argument of the log was e. So this is the same thing as this. I just replaced the ln with a log of e. So from here, we don't know what this is. We're trying to figure it out. So let's say it's equal to, x is already being used over here, so I'll just say it's equal to y. So now let's shift some things around with this log and write it as an exponential expression. I'm going to make that base bigger. I bring the y over, and that's the power. And then this e goes to the other side. And by the way, if you're confused on this process, on the whole evaluating logs thing, I have another YouTube video where I went through that. So what this log is actually asking me is, well, e to what power is equal to e? And of course, there we know that that power is going to be 1, right? E to the first power is equal to e. And so that means that the natural log of e, log base e of e, is equal to 1. So that's why it's nice to use natural logs when we have an e. And all right, so now let's move on to problem 5. Problem 5 gives us that 5 to the x plus 2 minus 3 is equal to 1. And this is a little different from the problems that we've been seeing so far. In this problem, we have that minus 3 that's attached to this 5 to the x plus 2. So there's multiple things on the left-hand side. And what we're used to seeing is just one thing on the left side, one thing on the right. So let's try to do that here and isolate this 5 to the x plus 2. And we can do that really quick by just adding 3 on both sides. Once we do that, we have something that's a lot closer to what we've been seeing. This is going to be 5 to the x plus 2 is equal to 4. And now let's check, can we get common bases here? Well, no. Between a 5 and a 4, definitely not. So now we're going to take the log of both sides. So we have log of 5 to the x plus 2 is equal to log of 4. And from here, we use that property of logs where we can pull that exponent out front, and we get x plus 2 times log of 5 is equal to log of 4. And now to solve for x, let's divide each side by the log of 5. And we're left with x plus 2 is equal to log of 4 divided by log of 5. And from here, the only thing left to do is just subtract 2 on both sides. And when we do that, we end up getting that x is equal to log of 4 divided by log of 5 minus 2. And there you have it. Problem 5 is done. And moving on to problem 6, we have this e to the 3 minus x, but it's being crowded by a bunch of stuff on the left-hand side. It's got this 3 that's being added, and then there's a 2 that's directly multiplying it. So let's get rid of all of that and just get this e to the 3 minus x isolated, and then from there, we can do our natural log stuff. So we'll start by subtracting 3 on both sides. And from that, we'll get 2 times e to the 3 minus x is equal to 7 minus 3, which is 4. We can then divide by 2 on both sides, and that will give us e to the 3 minus x isolated now on the left-hand side, and that's equal to 4 divided by 2, which is 2. So now, all we have to do, we can't get common bases here, definitely can't with an e, and since we're dealing with an e, we're going to take the natural log on both sides. So we have natural log of e to the 3 minus x is equal to the natural log of 2. Now from there, we've got this 3 minus x in the exponent. We can pull that out. and get 3 minus x times the natural log of e is equal to the natural log of 2. And well, we know the natural log of e is 1. That's why we take the natural log of both sides when we deal with e. So if natural log of e is just 1, then the left-hand side is just 3 minus x. So we can write this as 3 minus x is equal to the natural log of 2. Now from here, I don't know if anybody else does this, but what I would do to solve here is I would move the negative x to the left to make it a positive x, and I'd move the natural log of 2 to the left. And the reason why is because if you were going to solve it probably, I guess, the regular way and subtract by 3 on both sides, then you'd have to divide by a -1, and I feel like I just don't want to do that. So what I end up doing is I add that x over to make it positive, and I'm like, okay, well, I can't have this on the right-hand side if the x goes there, so I subtract it on both sides. So I don't know if I'm just weird, but that's how I do it. So on the right side, we have an x, and that x is equal to 3 minus natural log of 2. And for me, I would say that's a quicker way of doing it, but maybe you disagree. I don't know. Either way, the problem's solved. So now we're going to move on to problem 7, and this one is a little bit different because what we've been dealing with so far in the last 4 problems is we'll get something with a power with x on one side, but the other side won't have a power with x's. Now it does. So what do? Well, first, can we get common bases here between a 6 and a 2? Well, it might feel like it because 6 is a multiple of 2, but no, there is no way that we can get common bases. You might be thinking, oh, maybe we can make the 6 a 2 to the third, but 2 to the third is 8, not 6. 2 times 3 would be 6. So we can't do that. So what we're going to have to do, since we can't find those common bases, is take the log of both sides. And when we do that, we get log of 6 to the x plus 2 is equal to log of 2 to the 3x minus 5. Now let's use that property of logs where we can pull that power out front and multiply it. And we get x plus 2 times log of 6. And that is equal to 3x minus 5 times log of 2. Now from here, what we've usually done is, okay, well, we've divided that log of 6 on both sides, got that to cancel, and then we would just solve for x by subtracting 2. And that would work, but we have an x on the other side as well. So we're going to have to distribute this log through and then try to get our x's all on one side. So log of 6 times x, that's x log of 6. Log of 6 times 2, that's 2 log of 6. And then distributing the log 2 through on the other side, we have a 3x times log 2. And we have a -5 times log 2. So this looks pretty gross, but all we have to do from here is get our x terms on the same side. So what I'll do is I'll subtract the x log 6 on both sides. And that'll get all my x's over to the right side. And then I will get all of my non-x pieces to the other side. So that means I need to add that 5 log of 2 on both sides. And so going down the line here, the x log 6's cancel off. And then I have a 2 log 6 plus 5 log 2. And that is equal to a 3x log 2 minus x log 6. So now that we have our x's all on one side, what we can do is we can factor out an x, and that's what's going to allow us to really get the x by itself. So doing that, we're going to keep with that 2 log of 6 plus 5 log 2. And that is going to equal to, if we pull an x out, then what we're left with is 3 log 2 minus log of 6. Right, factoring out an x just means we're dividing each of these terms by an x, and when you divide each of those by x, you get these two things. And now x is being multiplied by this giant thing, and that's the only thing that's stopping it from being by itself, so we're going to divide that giant thing on both sides. And so your answer, you could write as x equals 2 log of 6 plus 5 log of 2 all over 3 log of 2 minus log of 6. And I say you could put your answer like that because a lot of teachers right from there, they want you to just put that in your calculator and give them the decimal. And that's fine. You can do that from here. But what I like to do is I like to limit the amount of calculator work I have to do. I would like to limit the amount of things I have to type into my calculator. And so if you want to do that, you can compact this a little bit. So this is up to you, but here's what I would do from here. I would take all these numbers that are out in front of the logs and put them in as the powers, right? This is just a property of logs that we can use. When you do that, you end up getting instead of 2 log of 6, this will be a log of 6, and that 2 gets pulled in and it's the power. So it's log of 6 squared, which we can write as 36. And then the second log, this is going to be 2 to the 5th power, which is 32. So that'll be log of 32. Then looking in our denominator, we'll have a 2 to the 3rd power, that's 8. And we'll have that minus log 6. And now that really didn't give us any less calculator work to do, but what we're going to do next will. If you look in this numerator here, we have 2 logs that are being added. And when we have 2 logs that are being added, we can combine them into one log. We just have to multiply their arguments together. So if we do that, we're going to get x is equal to log of, you don't actually have to multiply these two together, 36 and 32. Just do that in your calculator. Then in the denominator, we have 2 logs being subtracted, and that means we divide the arguments. So this gives us log of 8 over 6, or you could just simplify that. Just divide top and bottom by 2, and that'll give you log of 4/3. And now you have something that's a little less tedious to plug into your calculator. So again, you could plug that in, or you could go through and plug this entire thing in. It's really up to you. Now moving on to our last problem for this video, we have 2e to the 2x minus 5e to the x minus 3 is equal to 0. Now you might not notice the pattern we have going on here, but this kind of looks like a quadratic. And let me show you why. We can write this e to the 2x as e to the x squared, because we just multiply the powers here, that gives you 2x, and this is the same thing as e to the 2x. And let's just fill in the rest, the negative 5e to the x minus 3 equals 0. So now do you see the quadratic pattern? We have something being squared in the first term. We have that same something, to essentially the first power, in the second term, and that same something is missing from the last term. If you still don't see it, I'll make it a little more clear for you. Let's let u equal e to the x. And if we do that, then we get 2 times e to the x is u, so this is u squared. Then we have minus 5, e to the x is u, so this is just going to be a u. And we have minus 3 equals 0. And now you can see that quadratic. And we can solve that quadratic using the quadratic formula. And what we're going to get as our answer, that's going to be the solution for u, but we want the solution for x, so we'll have to use this conversion to actually get our values for x. So let's start using the quadratic formula here. To do that, we got to identify our a, b, and our c. A here is the number on u squared, that's 2. B is the number on u, that's negative 5. And c is the number without a u, that's negative 3. from there, we have that u is equal to negative b, which b is negative 5, so that's going to be a positive 5, plus or minus the square root of b squared, that's negative 5 squared, minus a 4 times a, which is 2, times c, which is negative 3. And that is all going to be over 2 times a, which is 2. So now let's simplify this a little bit. We get that u is equal to 5 plus or minus the square root of negative 5 squared is 25. And then we have two negatives here, so we know that this is going to be a positive. And we have 4 times 2, that's 8, times 3 is 24. So I don't know if you can see this yet, but we have a 49 getting set up under that square root. And from that, we'll get a 7. So yeah, in the denominator, that's 2 times 2, that's 4. And from here, we have a 5 plus or minus, again, 25 plus 24, that's 49, and the square root of 49 is 7. So that simplifies pretty nicely. And from there, we can get our two values for u. U is going to equal 5 plus 7, which is 12, and that divided by 4 is 3. And u will equal 5 minus 7. 5 minus 7 is negative 2, and negative 2 over 4, that's a fraction that you can simplify to negative a half. So here we get our two values of u, and we're not done yet. We still have to plug into our little conversion here, our little substitution that we made, and that'll allow us to find the values of x. So first off, we have that u is equal to 3, so we can say 3 is equal to e to the x, and I'll actually write that backwards. I'll write that as e to the x is equal to 3. So that way just things work out nicer and I have my x on my left-hand side. So from here, we know how to solve this. We take the natural log of both sides. So we get the natural log of e to the x is equal to the natural log of 3. We can move that x outside of the natural log, and what we're left with is x times natural log of e is equal to natural log of 3. And natural log of e, that's just 1, so we get that x is equal to natural log of 3. And so right there, that is one of our solutions for x. Let's look at our other one though, u equals negative 1/2. Well, for that one, if you plug that in, instead of e to the x equals 3, we have e to the x equals negative 1/2. And do you see a problem with this? There's no power that you can put e to. E's a positive number, right? It's 2.718 something. And when you put that to a power, there's no way that you can get a negative number off of that. So what that means is that there's no value of x that can make this happen, and so there's no solution for that one. So that means the only solution that I get for this problem is the natural log of 3. And that's going to do it for the last problem. So that is exponential equations in a nutshell, and if you're feeling pretty good with all of this, then here's a problem for you to try and answer in the comments. This is a pretty quick one here. We have 8 to the x minus 1 is equal to 2 to the x plus 2. So give that problem a shot. Let me know what your answer is in the comments. And if you have any questions on anything we talked about in this video, again, let me know in the comments and I'll try to get back to you as soon as I can. Now remember, I do have that extra video linked where you and I will go through and solve 12 more exponential equations. So if you're looking for more practice with that, especially if you have a quiz or a test coming up on that kind of stuff and you're looking to review, I highly recommend you check out that extra video in the description. And while you're at it, definitely snag those notes for this video as well. Lastly, make sure that you guys are subscribed to this YouTube channel because look, we're getting closer to 100K by the day. We're at like 71 right now, and every subscriber, every new subscriber gained gets me one step closer to moving out of my parents' house. And that's going to be great for both of us because you're going to get more videos and I'm going to get to move out of my parents' house. So anyways, that's going to do it for this video, guys, and I'll see you soon.